this long, so I'm quite happy to talk a little bit about my work. Today's talk is live programming requires enabling technology. And my name is Riemer van Rozen. I'm a postdoc at CWI in Amsterdam, and I work in the software analysis and transformation group. My research is on live programming and automated game design, and today I talk about both. So finally, after many years, the things seem to be aligning, and I'm quite happy about, well, being able to show you some of it. Let's see if I can also reach my slides. Okay, working. So I will talk to you first about a problem statement by introducing machinations, domain-specific language for game economies. Machinations was originally developed as a game design aid. Basically a nice tool with some visual syntax, but without a clear semantics that made it difficult to use the language for programming. So what the first thing we did was, for this visual language, we made a textual syntax as well. And I created a tool that would translate it into Promella so that we could do formal analysis of these models and make predictions with accuracy about what the code does. Then afterwards, we also wanted to make games using this. And one of our goals was live game design, namely modifying a game's mechanisms for prototyping, playtesting, and fine-tuning gameplay, which is a thing that is difficult to do in game development because of, well, basically software decay. It's very rapid in game development because every time you make a change, you fix something, and especially things related to gameplay cannot be fixed. They need to change all the time in order to find out what good gameplay is. So over the years, we made different tools for this. This is a pattern-based editor that would allow you to modify the code. This is an earlier version of a live editor, which worked on Unity. And well, basically, we had some issues with getting the code maintainable and understandable. We did several case studies. One of them was a tower defense game with creeps coming down the screen, and you could modify the towers and bases using this DSL. And the other one was a flyby shooter game where you could modify several parts of the game using the language. You'd had to pause it because otherwise, of course, you'd be dead before you could modify the rules. So one problem we had developing this domain-specific language over the years was that there is a general lack of enabling technology for creating live programming environments. And this is a recurring issue that made our earlier work difficult to maintain. So the objective, and the thing I will be talking about today in this talk, is to develop language parametric enabling technology that powers live programming. And I'm not going to go into the pitfall too much of defining what live programming is, but I will tell you about the approach. So the approach is to develop a framework called Cascade. Its name is derived from events leading to other events, like a cascade. And it's a meta language for creating languages with interface and feedback mechanisms that you need to create live programming environments. And there is a workshop paper on this work, and yeah, you can find that online. But let me go into live programming. So to explain a little bit about how this works, I take Norman's work on cognitive engineering and to explain the idea that live programming supports the understanding of the effects of programming actions with feedback that brings code to life. That's as close to a definition of live programming as I'm going to get. So programming starts with intentions. Good intentions, bad intentions, I don't know, it's in the mind. That's translated into actions. Of course, you type on a keyboard, you use some user interface to perform a programming action that has an effect on a working system. And this effect is good or bad, we don't know yet. It's displayed, and then you have to interpret if it's good or bad and evaluate the result. And live programming is about speeding up these programming cycles so that it's easier to comprehend if the changes that you are making are having the effects that you are looking for. So of course that can be done with probes, as it is done in live programming many times, but today there will be nothing about probes. There will be a lot of explanations about how the effects work that Cascade generates. If there's time for discussing more related work, I have a whole bunch of backup slides on this, but for now we keep focusing on the approach here. So the talk follows the structure of the paper, namely 4 challenges that I address with Cascade. The first one is to prototype live languages, between quotes. What is a live language? Well, that's a programming language that supports aliveness. So to design API and read eval print loop mechanisms for coding, user interaction, and feedback. That's the first challenge. The second is modeling languages, to create languages with abstract syntax and runtime state with meta models. I hope that many here are very familiar with that. The third is designing side effects, and that's about expressing coding actions. So these actions that I just explained in this cycle that I showed that work on abstract syntax, but also user actions that work on the runtime state. And in Cascade, you don't actually distinguish between those. And finally, and this is a very difficult one and a very important one, it is that Cascade helps you account for runtime eventualities. And that means that you can express runtime scenarios and runtime state migrations using Cascade by planning what will happen in the future and based on all kinds of conditions. And this is hard. It's part of language design. So when you design a language, you need to do that for it to be live. Normally with languages, you don't need to do that. You have a compiler, you generate a program, you run it again. But in this setting, we don't run it again. It's always running, and the changes need to propagate through the system as it is running. So the contributions of Cascade are mainly on the effects. But in order to explain that, I found out you need to show something visual as well, because otherwise people will just say, okay, I see a very long trace of events, but what does that mean? Yeah, okay, maybe you're right. I need to show something that we can all enjoy and understand. So that is what I will do today. I will go to a prototype of mine called V. Why V? Why is this prototype called V? Well, c'est la vie. It's alive, right? It's life. And V is a prototype, tiny game engine that allows you to prototype game economies and heads-up displays and play test running games. So all of that at the same time. I've asked Stable Diffusion to generate an icon for me, and I got a whole bunch, and my daughter picked the green one. So I like it as well. And the other icon is, of course, Godot, and we are all waiting for Godot, but it's a very nice game engine that you can use to make very nice interfaces, also for domain-specific languages, I found. So some of the design highlights of this prototype are live desugaring, which was somehow very difficult to do. Multiple languages running at once and interacting with each other, so the polyglot idea. And finally, fixed point computations. Live programming often requires that changes are propagated until they are done. And in order to express that, you need a definition of done and keep going until there's, while there are more effects. So that is also an important highlight of V. So I will get back to this, I guess, because first I would like to show you the demo. And later we can go back to this slide. Okay, now the next thing fills me with dread. Let's see if I can run the thing and if I can just, because I now have a lot of windows open, but can we see this? We can, okay. Well, this is V running. We're going to start by placing a node on this canvas. And this is a pool node. It's a place where you store resources, a little bit similar to Petri nets. But in this case, it stores the main character of our game, V. As we place it here, we get some side effects on the heads-up display language. Namely, we get a sprite and a label that are also added to our game. And finally, the game is already running, except that there's no V yet. The current state is 0. So we need a way for V to enter. Let's see if I can do that. And this is a passive node. I can make it an interactive node that has an effect. Namely, I get a button in the heads-up display. And I can press it, and there's V. See, entered the scene. But there is an issue. I can just keep pressing it, and she will arrive many times. That's not the idea. The maximum should be 1. Okay, we now have a way for her to be alone, and we need a way for her to leave as well. Let's do that. So this is incidentally a drain node. That's a place where resources disappear. The other one is a source node. That's where resources come from. So let's make this one interactive as well. We get another button in response. Let me just put them above. Yeah, we can also press that and also see it here. Looks good to me. We don't really need a label. Let's remove it. Okay, that's a good start. Let's add some currency to the game. The main currency of this game is apples. Why apples? Don't ask me. I'm the designer. I decided on apples. Apples come from a store. And every time V enters, we will get apples. Let's see if that works. Yeah, there's an apple. That's good. Let's make some more apples. Yeah, she brings us apples. Good. Okay. Actually, we can also click in the diagram here, which is a nice feature of liveness. Apples. Okay, there are some apples. Now, we can create some story here about V, who has apparently lost her bunny. And I have a 3-year-old daughter, so maybe I'm influenced by this. Bunnies. Okay, V will have bunnies, and she wants her bunny back, and she can exchange an apple for the bunny, and then live happily ever after, hopefully. Because as you see, these graph languages quickly get complicated. Well, what has happened? A whole lot, actually, a whole lot of side effects of, we have a new button and we have new labels. We don't really need the labels. So let's remove those. But we have a button for her to swap an apple for a bunny, and success. She has the bunny. So we can check our game economy here and see if we can swap it more. Actually, I have the same problem as before. There should be a maximum of 1 heart, and we don't need more than 1 bunny. And maybe we want to add that when she leaves, she takes the bunny. And that would make all well that ends well, I guess. So what we see here is that we have a game economy that we can adjust while the prototype is running. We can edit, we can introduce currency. I have done it in such a way that all these names just appeared in this order, but actually they're all adjustable. So via this editor, we can adjust the behavior of these nodes. And as you adjust the behavior, actually the heads-up display can change and the running game can also change. So there is no button yet for restarting the game as we created. But it already has a significant subset of the features of machinations that will allow you to very rapidly prototype a game. So I think I'm relatively close to what Raf Koster, a famous game designer and a speaker at game conferences, asked. He said, it needs to fit on the back of a napkin. Well, it's not quite a napkin, but it's close, I think. So yeah, let's conclude the demo here. I think it's kind of clear what it does, right? Yeah, okay. So we go back to the rest of the presentation. Nothing crashed. That's amazing. It kind of works. So what we've seen happen is actually that when V entered, she brought an apple. And that was a trigger of another event that you could add to this model. And under the hood, the language actually has a fixed point computation that triggers other nodes to activate and then run the effects of those nodes as well. So you can make a whole series of triggers of nodes that succeed, that trigger other nodes. And well, yeah, you can do it cyclically as well, but of course, then it won't return and our UI will be stuck. But the point is that the fixed point computation works. So is this a lot of work to program? Well, it was a lot of work to invent Cascade, but not a lot of work to make machinations again, because, well, I've built that language so many times. So the number of lines of code, we see that the diagram language is still less than 1,000 lines. The runtime state language, which actually keeps the running game state, is approximately half, and then there's the heads-up display language, which is 300 lines of code approximately. But when we generate it, it gets significantly larger, and well, creating this language in Godot, it requires some extra C# code to make that working. So let me bring you to a slightly smaller example, and I'm sorry I have to do this, but I'm bringing you to a smaller example in order to explain also how the meta model works and how the side effects work. And this is another language, the TinyLive state machine language, which is especially developed for presentations as a running example. You can also put it in papers and such. So we're going to simultaneously program at the top a state machine, and you see the running programs at the bottom. In this case, instead of having user interface elements where I drag and drop and use a UI, I'm running the events manually. So I don't have a beautiful UI here yet. This was a first version, a web UI that I presented at the live programming workshop. And what we see happening is that we create machine doors, we create open and close state, and then we run this machine, which is initially in the open state, and then trigger the close action, and we see that the state becomes closed. The little star shows that it made a transition. And the brackets where you see open, that actually signifies a button. Well, maybe I should have made this one in Godot as well. It would look better, I think. But on the other hand, this very clearly separates the syntax from the running instance. And the demo I showed before integrated the two that made it perhaps less clear that there were multiple models running at once. So we see the abstract syntax and we see the runtime instance. Okay. Now what we're going to do is to add another state. The machine is already running, of course. We have a running instance at the bottom. But we add a locked state and we see we get an initial count of 0. And we're now also going to create transitions for locking the running machine, and then trigger it as soon as it is added. And we see that the current state becomes locked. Now, what does this tell us? That means that we can modify running state machines and activate running state machines. So it means that the runtime state has to migrate with the program. Now, what would happen if we delete the locked state? Well, you see that at the bottom, we end up in the state opened again. Well, why is that? That is because that is how our language works. It's the language designed to say, if a running machine instance doesn't have a current instance, go to the first one. And well, is that correct? Is that wrong? I don't know. It's part of how this language is programmed. It's not to fix the program. It's just that when you have a live language, its semantics needs to include those kinds of things. So how big is this? Well, this tiny example is 213 lines of code in Cascade, but the compiler makes 2,200 lines of C# out of that. And I want to show you a little bit about how this thing works under the hood, because of course we're at a Strumenta talk and it's always nice to also show something about the internals. So at the beginning, I talked about these 4 points that Cascade addresses. And we're going to start by looking at how it helps prototyping live languages and to help you to design API and REPL mechanisms for coding, interaction, and feedback. So first of all, the compiler. Who loves tombstone diagrams? I always like them, right? Tombstone diagrams. Well, in case you don't know them, the little mushrooms that we see here, this is a program, in this case, L, written in TEL. TEL is the name of the language that Cascade offers. Transformation effect language, not a very good language name, I know, but it's input to the compiler. The compiler is written in a meta-programming language called Rascal, and it translates TEL into C#. And when you compile it, what comes out is the language written in C#. So the Cascade compiler reads Cascade specs and generates C# language prototypes that integrate with the other part of the framework, namely Delta. And the compiler, the most difficult part of the framework, is written in Rascal, and it's 2,600 lines of code. It's very hard to compare this, but it's extremely condensed because you can transform big syntax trees in Rascal without too much effort. So these 2,600 lines are quite, well, a lot for such a compiler. So what actually happens is that you get a generated language prototype that under the hood also generates, well, I'm saying Delta here, it's actually edit operations. And what comes out is a generator. Yeah, it generates a generator that when you run the language, it interprets events and generates edit operations. And these edit operations are used to enact the effect and to commit to the history what has happened. So actually, what the Cascade framework also does is to give you a complete history of all modeling actions of all programming actions, and yeah, an account of the history. So instead of having to commit that in a textual way, in a lossy manner, we have the high level differences, and also, yeah, a way to trace changes. And some other weird new components that it has is pre and post migrators. So why do you need those? Well, you need a pre-migrator for pretty much anything that needs to happen before an event happens. So you can schedule an event, and if you need something to become ready for that event to happen, then you can schedule that and make that happen first. So that's not so different from a destructor, actually. Like in object-oriented programming, you have a destructor, and when you delete an object, that's what happens first, right? In this case, well, you often use these pre-side effects for destroying things, cleaning things up, and post side effects are, well, very similar from how it normally happens when you call a method, things that happen afterwards. But instead of getting stack traces that are removed afterwards, in this case, we also have stack traces, but we have a result, namely a history that has all the committed events. And yeah, and these migrators, they are called by Delta's runtime that enables making user encoding actions. The Delta is an extensible engine that interprets events and enforces change. It has, of course, a scheduler that schedules these pre and post side effects. It has a patcher. Oh, let me first show you the scheduler. How does this event scheduling happen? Well, first, for each event, it has to resolve the language. I told you that that V has a polyglot setup with different languages. When you schedule an event, it needs to find the language. Then it needs to pre-migrate the event if it has anything that needs to happen before. Then it calls this generator component that makes edit operations that allow you to commit to history what has happened. Then it post-migrates, and then it completes. And of course, this is a recursive algorithm. So with the pre-migration, it means that it makes events go first. But the weird thing is that you can schedule an event that has side effects that happen before your event happens as a result of that event being scheduled. So this means that given a Cascade specification, you can get yeah, resulting sequences of events and output that you can understand locally, but it has a global result that yeah, sometimes is surprising. And I will show you an example. So the patcher is another component that interprets the operations and commits transactions to history. And the dispatcher just relays the events to the right language. Now, let's look at TinyLive SNL again. So here's its abstract syntax using a class diagram. We see there's Mach, that's the machine, it has a name. It has a number of elements, those are states, those have names as well. And state has a number of transitions of input and output. And of course, each transition has a source and a target state. Nothing spectacular so far. Actually, it's a very small language. But there is also a runtime meta model. And the runtime meta model adds instance information of running state machines. And we see here that one machine can have multiple machine instances, and each machine instance has a defining machine. And also it has a current state instance, which also has a count. And of course, each state instance is defined by a state. Now, there's a simple notation for this. I stuck closely to object-oriented notation in order to express these things. Now, how to design side effects? When the programmer creates state machine doors, what actually happens is that the effect programmed in green here is called. And it looks very much like a method. It's not, because what's in the body of this effect is edit operations. You can't see that because it's translated from something very close to object-oriented notation. For instance, when it says m.name is name, what it actually does there is to say that the field name of an existing object, its value is replaced by the input name. So actually, you cannot just set something. It always replaces a value. And this is important to know, because when you commit such an event to history, such an operation to history, it means that both the old and the new value are there. Each operation can be inverted and undone. So effects consist of edit operations. And there's also the notion of bidirectionality. So for each thing that you create, you have to be able to delete it as well. And actually, we see future and past keywords. I needed those in order to generate the correct code, because a past keyword promises that an object in the future will no longer exist, whereas a future keyword denotes that an object will exist in the future, but does currently not yet exist. So this adds context to the Cascade language for me to know how to generate the code in the compiler. So why am I putting all these fields on null and deleting them at the end? Well, in order for it to actually be bidirectional, I have to do that. Otherwise, it doesn't work. And of course, I can only delete the states and the instances when there are no longer any states and instances stored. And if we think about that, that is because if I delete a state machine, it will delete from the top the whole containment tree of a state machine. But if I would invert that and run it in reverse, I would get back my current state machine, which is a feature of this kind of language design, which is also a nice way to implement save, by the way. So the clause below is a pre-clause. It states that before it can be deleted, it also has to delete all its constituent objects, the objects that it owns. So actually, in this case, you have to think about ownership a lot, like before we had memory management. Well, if you're used to programming in C++ without memory management or old embedded C, you of course you have to malloc and free everything. This is very similar to that, except there's no way around it. I cannot create a memory manager that does this for us, because it will hide all the effects. And the whole goal of Cascade is to make the effects explicit so that you can program them and give it side effects. So, okay, side effects. Now, you can also account for runtime eventuality. So how does that work? Well, we deleted this current state locked. And in response, the TinyLive SNL language removes and deletes the locked state from all the program instances, and it reinitializes all of these instances, which results in a migration if and only if a machine no longer has a current state. And how is that programmed? Well, we create an so we have an add state. The inverse is remove state. That makes some sense. It's very simple. This is just an edit operation that removes that state. But before it can do that, it has to clean up its mess, so to speak, go to all the machine instances, get all the state instances from those and remove them. Okay, and delete them, and then reinitialize the machines. And as a result, you migrate the running state machines to have a new state if necessary, so that all these different eventualities of machine with and without current states, they will all reinitialize correctly in response to the changes to the abstract syntax, to the program. So what does that look like? Well, basically it generates this. It's also in the paper, but it's a rather lengthy side effect of just removing the state, the current state locked. But we can kind of see here at the bottom that it reinitializes, that you get a new current state. And well, I want, of course, this language to look more like Cascade itself. At the moment, it actually has the universal IDs shown there, but you also see the current values of bringing the count from 1 to 2. You see here, you also see that the name of locked goes to 0. Oh yeah, here at the end, we actually see the locked state being deleted. That was the thing that we ran. We deleted the locked state, but that actually happens last. We can't delete it until all the running machines are migrated. So we see that the pre-migrators ran. So the objective was to develop language parametric enabling technology that powers live programming. I've shown a little bit about Cascade, a language for creating languages with interface and feedback mechanisms for live programming. I've gone over these 4 elements for, let's say, challenges that Cascade helps solving. There's a whole lot of other challenges that it helps solving that I can't really put into words that well yet. That's also because I'm still writing the paper on this. I have a workshop paper, but I need to write a conference paper on this. I'm thinking about software language engineering as a conference to submit it. So what I have shown you is the little game engine V, which includes machinations, the heads-up display language. But there is another language that has similar side effects, which is LiveQL. Thijs van der Storm developed a questionnaire language for the Language Workbench Challenge, and he created a live version of it. It's a rather, well, it's a piece of work, let's call it that. And I was able to translate that into Cascade. And now I want to build, of course, a nice visual interface for it so that we can also see that one run in Godot, or maybe make it a web UI, I don't know yet. And aside from this, I will also work on visual REPLs and generic live IDEs. Cascade is screaming for a debugger, really. It has so many levels of abstraction. If something doesn't work, I have to think in several abstraction levels in order to fix things. So that's rather difficult. This concludes the first part of my talk. I have a whole lot of backup slides in case we have some time, or in case there are questions about it. So for instance, some related work slides, if we want to have a look at edit operations, for example. What else do I have? Model transformation languages, the history of machinations, and the meta model of V. But anyway, let's just first give you a chance to ask a question. Thank you all for coming and for paying attention.
Thank you very much, Riemer, for the very interesting presentation. So, do we have questions?
I think there are a few in the chat.
I'm trying to get the chat window, but where did my chat window go? Ah, found it. Okay. Who's first? Because there's a lot of messages. Let's see. Did you look at literature on lenses and functional optics? Not yet, but thank you for the suggestion. Perhaps you want to comment on how this relates? Peter? maybe not. Let's see. So it's definitely not immutable. I need mutable data, and I've had long conversations with Jurgen Vigneault about making this an immutable data approach, and we ran into several problems that shared data structures, how it would work under the hood. So let's say it's an open question how this can be done. Let's see. Oh, there's so much here. Can we see this as a branch of AI programming? Well, no, because what we have here is actually a programming language that responds to change. And when we think of these using large language models to transform programs, that could actually run on top of this, just as it could with other programming languages. I've seen several people tweet about how this kind of stuff integrates very well with DSLs. Many DSLs have a nice textual notation. Well, this has as well. So I suppose you could use those models to also help you create diagrams and create and program, but it won't actually help you to design the side effects that your programming language has. So you have to design those yourself as a language designer. And I don't think that is that AI can do that, because it doesn't have examples of how this kind of migration should work. Okay, let's see, what else? More questions? So many things I didn't talk about is how these edit operations, what they look like. That's something I could still show. Let's see. So
I also remember that you named model transformations.
Transformation languages. Well, I ran into Janus or Janus. I'm not sure how to pronounce it. I really want to learn more about it. I think that especially the change propagation that it offers is strongly related. But I've not found if JTL has been used for live programming settings. Is there information on this? I'm actually curious. I have such a knowledgeable audience.
I'm totally ignorant about model transformation languages, and I would like to learn more, because we could use them in the context of writing transpilers. That is something that we're spending some time on. So I'm always learning for
Right.
waiting for pointers. So maybe I will take a look at Janus, or maybe.
Yes. Well, the language I use is Rascal for building the compiler. And well, the selling pitch is it's a one-stop shop for meta programming, but it allows you to do many things like develop DSLs, make your own grammars, parse it, concrete syntax, abstract syntax, matching, of course, transformation. It helps you analyze source code. If you have an existing front end, you can parse it and analyze it. And basically, it allows you to glue tools together. If it isn't integrated, you can attach it, or you can make new libraries. And it's used in teaching in many universities. And in this case, I use it to build a prototype compiler. And without Rascal, I am not able to prototype this compiler. It would be too big. I would be struggling too much with making changes. So having Rascal as a tool to build languages is extremely important for me as a researcher. And I know that Rascal is also being used by SWOT Engineering, which is a kind of a spin-off company from the research group that is also using Rascal in with bigger businesses in other countries, which is, I think, under NDA, so they can't talk about what those businesses are. But they are doing well with Rascal, and it's also giving them a chance to develop Rascal for research and for practice. So it's my let's say it's my hammer, and everything now looks like a nail, but it's a very versatile hammer. You can do a lot of things.
So if one has to pick a hammer, that is a good choice. Yeah.
I think so. It's the language engineering workbench hammer. I don't know. Yeah. So
thank you.
So yeah, well, edit operations. I don't know if you know these, but they are bidirectional operations. I derive them from Alan and Porres, their seminal paper on the difference and union of models. And Thijs van der Storm was the first to identify them as useful for semantic deltas for live DSLs. And yeah, that it works. So I'm using them as the low-level implementation of change. But the events that are running in Cascade encapsulate these low-level changes. But it's, yeah, basically you have a create, it creates a new object, and then the inverse of that is delete. Normally, you, of course, don't have to say which class you're going to delete, but it's sort of an implicit parameter, because if you invert this, it does the exact opposite, right? And yeah, so this is kind of important. The same with list modifications, that you have an insert, that you have a namespace query. It operates on a list that sits there, and you say at this index, insert this value. And then you need an opposite for undoing that. And yeah, there is an instruction for that as well. And then set is its own inverse, because you set a value at a certain index, you replace the old value by the new value. And so each of these instructions, you see an inverse for it. And this is what I run at a low level. And this is actually just, I don't know, 200 lines of code, 300 lines of code. It's small, but yeah, it needed to be correct in order to, yeah, store the changes. So that, yeah, that's kind of, I didn't put it in a main talk. I thought this is kind of separate from it, but yeah. And I think I should wrap it up, really. So if there are some more questions about other topics, I would be happy to answer.
Okay, then maybe I will stop the recording so that if somebody wants to ask questions freely, they can do it offline. So I will just stop it.